So this lecture is about graphs and what you can learn from them. Different kinds of graph, all of them relating to motion. We have already talked about some of the graphs, but now we will just talk about the graphs. So for the first graph, we will use the DT graph. And the DT graph is a graph of the distance traveled on the y-axis and the time taken in the x-axis. This is probably the easiest graph to understand because you have an intuition about how it works from your experiences in real life. Yeah, and I already said we have the distance on the y-axis and we have the time in the x-axis. This means that we can always read the position from the starting point at any given time. So if I say at 5 seconds, how far away from the starting point were the different kind of motions? So now we have motion 1 and motion 2. And we can read out exactly how far from the starting position everything is. The slope of the DT graph describes the velocity. So for a linear graph, you will always have a constant velocity, and we can use the y equals kx plus m formula to decide the velocity is the k value, the m value is the starting position, and time is the x value, and y is the distance traveled. If we have, I already said that, right? Yeah. And if we have a line that isn't linear, like it's changing, like the blue one, that means that the motion isn't constant. We have an acceleration or a retardation of the motion. And in this case, we have an accelerating motion because we can see that the inclination of the graph is increasing. In these kinds of motions, we will often use the tangent line to describe the momentary or the instantaneous velocity at that point. Can all of you decide the tangent line? This is something we need to explain. Yeah, so for this graph, we have point A, and I have drawn a tangent line to that. And to describe the instantaneous velocity at that point, we used the delta t and the delta s and the delta d for that inclination. So you take the difference in distance divided by the difference in time, and you get the momentary or the instantaneous velocity. It's often most easy to choose points on that tangent line where we have 0 on one of the axes. For example, you can see that this point is, we have 0 on the y-axis at 3 seconds. So we use that because that gives us a more easy expression to calculate. So this is useful trick or hack if you want. We also have what's called VT graphs, and they're similar to the DT graph, but instead of distance on the y-axis, we have the velocity on the y-axis. And from these kinds of graphs, it's possible to derive more information than the DT graphs, just because you have two relations between the y-axis and the x-axis. Because the x-axis is velocity and the x-axis is time, we can get a quotient between those. So we can get the velocity divided by the time, and that is defined as the acceleration. That gives us that the slope of a VT graph is always the acceleration at that given point. So from this motion you can see that from the beginning, we have a positive acceleration. At the top of the graph, we have no acceleration, we have a constant velocity. And then we have a negative inclination that gives us that we have a retardation on the motion. Everybody understands this graph, right?
Yes.
But the other relation we can use is that you can also multiply it. So instead of dividing the axis values, you can multiply the axis values. And then we get this useful formula that is the velocity times the time equals the distance, or as in Swedish we use sträcka. Therefore I'm using an S in this case because the recognition factor. So when we have that, we can divide any given VT graph up in segments. And each segment is contributing to the total distance traveled. And I will use the simplest kind of geometrical structures I can when I have these kinds of graphs. So what we're good at rectangles and we are good at triangles. So if we can divide the whole area under the graph in rectangles and triangles, we can solve for the distance traveled. So yeah, and the thing is, we use all the regular geometrical formulas for calculating the distance. So if it's a triangle, we use the formula for a triangle, like we have the base times the height divided by 2. If it's a rectangle, we only have the base multiplied by the height, and so on. If in some weird, we had like, what else do we have like a formula for? So if we would, in a weird three-dimensional moment, have a like circle, we would use the formula for a circle. So all geometrical formulas that can be used is usable. Any questions about this?
Will there be any like curve or?
Not in Physics 1, because you can't integrate stuff yet.
Okay.
But if you can describe a graph or a motion as a function that you can describe in one variable, you can always integrate and will get the area under the graph. So if you are at that level mathematically, it's fine. Any other questions? Then we move on to the third one. And that's 80 graphs. And following the same pattern, we have that 80 graph is acceleration time graphs. Therefore, we have acceleration on the y-axis and time on the x-axis. And these graphs are probably the hardest graph to interpret, because we have no way of really connecting them to our own understanding. Yes?
Was it the same as, what was the benämning on the graph before?
The name of the graph.
No, the y was acceleration.
For the last one was velocity on the y-axis, and this time it's acceleration on the y-axis. For all these graphs, it's time on the x-axis.
Okay.
So these are the ones that's most hard to interpret. So if we look at this graph, we see that we start this motion with an acceleration with just under minus 10 meters per second squared. And then we have a change at 4 seconds where we decrease our acceleration. So we're starting to accelerate slower. It's not that we aren't having an acceleration, it's just that the acceleration process is slower. And then at 6 seconds, the acceleration is 0. At just that second, we have no change in velocity. And then on the positive side, we have a positive acceleration. That means that we are now increasing our speed compared to the 0 point or the negative value. So could anybody give me an explanation what this movement could be? Like what could that motion be?
Okay.
So if I say the value that's just under 10 meters per second square, what could that value be? If I say perhaps 9.82. Yeah, that's the gravity. That's the acceleration of gravity. And from this you can deduce that we have defined positive axis upwards and the negative axis downwards. So we're accelerating, we're falling here. This is a falling motion. And then during the blue one, what could happen here? We are decreasing our acceleration. That, yeah? Could be a parachute. Could definitely be a parachute. Could be something else.
It's like you spread out your body.
You could spread out your body and decrease the acceleration that way. Most likely, as we see that we have a positive acceleration, that means that the motion is accelerating upwards also. So probably this could be like a ball bouncing or something like that. So we have like falling, bouncing. During the compression time of the ball, the acceleration is decreased, and then it accelerating upwards again. That's something that could happen, for example. If there were different time periods, because this is a very, very, very long time for a ball to bounce, but that could be the kind of motion we can think about. So that's just to look at the graph. What can we then actually get from this graph if we want to do calculations? The slope doesn't give us any useful information like numerically, because what happens in the slope is we have an acceleration divided by time. So the unit for that would be meters per second cubed. We don't have any physical realization of what that is at all. But the area on the graph is delta V, because we have the acceleration multiplied by the time. And that is the definition of delta V. So this is a change in velocity. So from this graph we can also see, like for the green area we have basically minus 10 multiplied by 4. That, what did you say? That's about minus 40. That means that we will decrease our velocity by 40 meters per second during that time. The next speed we have 4 to 6, that's 2 seconds. So the base for that triangle is 2, and the height is basically still 10. So we have 10 multiplied by 2 divided by 2. So it's a decrease of velocity by 10 meters per second. And the third one.
But isn't it an increase from the velocity that came before?
Yeah.
It was minus 14 then minus 10.
Yeah, so it's total during from the starting time here, the starting time given, we have decreased our velocity by minus 50. And then we're increasing it by 10, because we have 2 multiplied by 10, 12, 24 divided by 2, so it's 12. So that's what we can actually get from it. But we don't know anything about starting position. This graph doesn't give anything about the starting position. The starting position could be up in space, it could be 10 feet from the ground. We also don't know anything about the starting velocity. The starting velocity could be 0. It could be 1,000,000 miles an hour. We don't know. So that's basically what we use the AT graph for. It's to try to explain motions and try to calculate the difference is in velocity. Let's do an example. So this graph, it's an VT graph, and it shows how Filippa changes her velocity when she's out biking. Use the graph to answer the following questions. What was the average acceleration between 0 and 2 seconds? What was the average acceleration between 2 and 6 seconds? What was the average acceleration between 6 and 10 seconds? And the last one, describe the motion in words. So the first one, can anybody...
5.
What?
It's 5, isn't it?
We're asking about the acceleration, not the velocity. So what is the acceleration the first 2 seconds? What? It's 0. We have no change in velocity. So the speed is the acceleration is 0 in this interval. Yeah, since the velocity is constant, the acceleration is 0. For the second interval,
Ska man ta den här formeln då?
then we're using the formula, right?
Right, so
We have-
delta V and delta T.
Yeah, we have delta V and delta T. And what is the difference in velocity?
Then
The difference in velocity is 10. And how long does it take?
2 seconds.
4 seconds.
Oh,
So you have 10 divided by 4, and you get the acceleration, the average acceleration. Okay. So it's basically 2 meters per second squared. And between 6 and 10 seconds, we have a decrease in velocity. That's a retardation. So we're decreasing our velocity from 15 to about 11, and it takes also 4 seconds. So we have this, the end velocity, which is 11, minus the starting velocity for that period of time, which is 15, and we divide that by 4, and we get minus 4 divided by 4, which is an acceleration of minus 1 meters squared, or if you want to express it as a retardation of 1 meters squared. And now describe the motion with words. And this, we have an infinite way of doing it, but this is my approach to it. So Filippa has a constant velocity of 5 meters per second for 2 seconds. After that, she starts to accelerate with 2.5 meters per second squared for 4 seconds. And finally, she starts to brake, which will result in a retardation of 1 meters per second squared for 4 seconds. That's one way to describe it. And that's basically all of the theory for this lecture. Do we have any questions?
No.
Was it understandable?
Yes.
So now I would like you to work with the section for AT, VT graphs, if you can. If you're not there yet, it's fine. You can still be working like for just acceleration or just the distance formulas. Next time we'll go through the more useful distance formula for all motion with constant acceleration, and that means acceleration equals 0 or positive or negative acceleration.
These ones.
Yeah.